this year's Southeastcon Hardware Team. Southeastcon is a IEEE conference where students and professionals get together and they share technical exhibits, sessions, and student competitions. The highlight of the competitions is the hardware competition. This is where students design and build an autonomous robot that meets that year's challenge criteria. To give you a brief history of Southeastcon and UNC Asheville's participation, I'll walk you through a few of the games. Last year, the challenge was to navigate on a line and play games as if you were on a road trip, things like Simon Says. This is the robot that team designed for that year. The year prior was a targeting and firing system of Nerf darts, and it also involved navigating on a line. The year prior to that was a shipping container crane that I'm standing in front of, and there's the robot for that year. This year's challenge was another shipping container crane robot. This is the game board for that year, and here is our game board with our robot for scale. Very big. The challenge here is for the robot to drive through a tunnel and collect shipping containers along a shipping barge. You distribute these containers to a truck, rail, to a boat, and to a truck. And you have to do all of this and move back to your home position in just 5 minutes. This year's challenge was exceptional, and it really pushed the design phase. Our development started early last fall with brainstorming sessions. We met weekly and just discussed some ideas for how we might tackle this problem. By the end of the semester, we had a conceptually complete design and a team locked in place, ready to go. Our design phase ended up being stretched all the way into about February, and it was probably early March before we really seriously started building. We knew at that time, for the complexity of this robot, a month was not going to be enough time for us to finish building and debugging this robot. We gave it the best we could, gave it a good shot, and the team decided that unfortunately, because we were unable to meet our goals for the year, we chose not to attend competition. However, there were many valuable lessons learned and a tremendous amount of experience gained from this team. To give you an idea about this robot, a top-level description is, this is going to sound like words, a holonomic drive chassis with a 5 degree of freedom manipulator arm, a 15 degree of freedom gripper assembly, with a single power supply, 5 regulated voltages, over 50 sensors, 25 motors, and 12 microcontrollers. Everything you see is completely custom. There's no kits involved. Meet Ripley. So this team designed and built, now debugging, a robot that fully met this year's challenge criteria. My team is here to outline that design and share some of their experiences along the way. Please join us next door after this if you'd like to see a mini demo we have set up. So to start off, we're going to turn back the clock a little bit and talk about our early phases of development, starting with some of the test benching that we had done.
My name is Fiona Popp, and I was a member of the programming team. One important aspect of this project was test benching the components that were going to be used on the robot. And test bench is where you take a component and you determine how the electrical, mechanical, and programming aspects work together. Testing the components allowed us to determine the best choice for a specific task and to provide proof of concept. All of the motors and sensors on Ripley were test benched prior to actually implementing them. For the navigation of our robot, the sensors and programming tools that were used were ping sonar sensors, a Pixie camera, and the processing IDE. For the gripper, color, current, and IR sensors along with servos and buttons were test benched. And for the arm, limit switches were tested. One of the test benches that took the most time were the motor drivers. We used DC motors for the navigation of our bot, and we used stepper motors for the movement of the arm. Choosing drivers is important in order to ensure that the motors are controlled efficiently and accurately. Overall, test benching is crucial for developing and proving design concepts. And through test benching, we have learned how to understand data sheets and pinouts. Not only was the wiring of each individual component determined, but we also had to design the circuitry in order to connect all of these components together.
Hi, my name is Murphey, and I was the electrical lead for the team. So mapping out all of these connections, this is what we call the plumbing. So this robot required a lot of planned beginning, as there were a lot of components that needed to be, we needed to communicate really well in order to figure out how everything was going to be connected, everything was going to be wired. So we used this this tool called the Schema tool, which we got from DigiKey. It's totally free, by the way. Free things are nice. So just talk a little bit about this wiring diagram. The master that you see in yellow operated 11 different slaves, and they're all in blue. So up here, you'll notice on Ripley that we have 4 gripper mods, and they're right here. So in each gripper mod, there are a button, there's current sensors, and there are also color sensors and servos. Down here is our drive system. Again, 4 slaves operate the 4 wheels. And over here is the arm, where we have stepper drivers, which operated the arm's movements. And we also had, various other contraptions and things that we had to add later. So we learned how to use this freeware called Eagle in order to make our very own principal circuit boards, also known as PCBs. So you'll notice here on our old chassis, this is like Ripley 1.0, the wires are a little bit cumbersome, they're not very organized, and in order to debug, you kind of have to, squint, put your glasses on, and, hope that you got the right one. So with the boards mounted onto the chassis, this is Ripley like, what, 8.0? The wires are much more organized. They come from one centralized area. You can see there's a board right here and board right here. And it's much better for organizing and for debugging later. They just look better. So how all of these boards connected to each other is we bought standard Molex connectors of various sizes, and we got wire and we crimped them and we made them ourselves, and these are all of what these little plugs are on top. All of these boards are all over the chassis, and that's what Kyle's going to talk about next.
All right, my name is Kyle Ward. I was part of the electrical team for this project. But the beauty of being a mechatronics major is that you can work on all aspects of the robot and not just a single one. So I got to spend a little bit of time in the design and assembly phase of the chassis. And when we approached this, we had to go a little more in depth than you would in your intro to robotics courses because of the sheer weight and size requirements of this robot. Fully assembled, it weighs roughly 35 pounds, so we had to make sure we picked out wheels that wouldn't break under that load. We picked out some Mecanum wheels that had a 33-pound max load per wheel, so we knew whatever weight we put on top, they would be able to hold up. And they also give us a wide range of motion. We could either travel forward, backward, side to side, or even diagonally if we wanted to. Another component that we had to look into was the motors that drove it. We had to make sure they had a high torque capability, that way we can maneuver around the board in a timely and accurate manner. Now, as you can see, there's a lot going on this chassis, a lot of components that had to fit in a small amount of space. We used CAD software to make sure that everything was going to be able to clear, no electrical components weren't touching anything they weren't supposed to. And we also had to take into consideration the ease of assembly. We learned more and more how important that was as we assembled the bot. There was a lot of components where they needed to be replaced or fixed, and they were very difficult to get to or required the removal of other components in order to get to them. So that was something that we learned. But when all was said and done, everything fit into the 12-inch by 12-inch by 5-inch footprint that we needed it to in order to get plenty of space for the arm and gripper on top. And Steve's going to talk more on that.
Thank you, Kyle. My name is Stephen Hay, and I was the mechanical lead for this project. Ripley's arm was constrained to fit into a 7-inch by 12-inch by 12-inch footprint with the gripper attached. While fitting into these constraints, and be able to extend to the maximum allowable tolerance of 20 inches cubed. While fitting into these constraints, the arm must have been able to meet all the challenges of the game board. For Ripley's arm to be able to lower the gripper into the box truck and raise to the tallest barge, our arm needed to have 2 y-axes, as seen here in the videos. Her arm also needed to be able to reach behind the rail car, so we needed 2 x-axes to do that. During the design phase, materials had to be chosen to handle the forces and moments that the arm would experience during competition. We chose extruded T-slot aluminum bar, square bar, as a translational support system while using self-lubricated bearing plates to create a near frictionless system. To limit the weight of the rest of the arm, we used aluminum forms and aluminum plate. The CAD model of Ripley's arm consisted of more than 125 pieces and resulted in many hours of labor. The biggest lesson we learned from Ripley's arm, bringing Ripley's arm to life, was that manufactured parts may not arrive when and how you expect them. This required us to shim and modify components that work completely well in the CAD model, as well as fabricate parts that did not come in on time or as we had specified. One of Ripley's other components that relied heavily on CAD was the gripper assembly.
My name is Ross Heninger, and as a mechanical engineer for our team, I shared the responsibility of advising how our robot would physically interact with the board and with the game pieces. Since all of the points in this competition stemmed from the organization of these blocks or shipping containers based on color and their original location, it was important for us to determine a quick and efficient way to pick up as many blocks as possible while simultaneously keeping track of the colors and where their original locations were. We originally were hoping to use vision processing to keep track of all the colors of the blocks that we have picked up. But then after some determination and some testing, we figured out that the readings varied a little bit too much based on the ambient lighting in the room. So then we decided to use an RGB sensor. This is another type of color sensor that provides its own light source in order to interpret or scan the blocks in order to store the information about what color each block has, or each block is. We then needed to figure out a way to align our crane with all of the blocks, and we decided to use infrared sensors and look for a feedback pattern of high and low blocks in order to align ourselves and then drop down to pick up the blocks. Once we figured out what sensors we would use, we needed to determine the fastest way to pick up as many blocks as possible while having a reasonable amount of trips to and from the barge. This was important because time was very limited in this competition. After some calculating, it was determined that 4 columns of blocks would be needed to be picked up at one time in order to successfully navigate the board in 8 trips, which would leave 50 seconds per trip. This seemed like a reasonable amount of time. This presented unique dimensional constraints on our robot that my partner in developing the gripper, Christian, plans to elaborate more on.
Thank you, Ross. My name is Christian Newhan, and I was on the mechanical team focused on the gripper. So once we had the challenge at hand and the concept in mind, we figured out the parameters required for achieving this challenge. 15 servos, 12 color sensors, 14 IR sensors, 4 switches, and of course, 129 wires. Also, the gripper needed to be able to extend to 10 inches to grab the blocks and retract to less than 8 inches to enter and release the blocks inside the truck. In our final design, the combined thickness of our 36 fingers was 1.25 inches. Two of the things that benefited us greatly and that our department graciously provided was CAD software and excellent 3D printers. This gave us the ability to do rapid prototyping. Once we had the design that met our very stringent requirements, we were able to print, test, and constantly optimize our 3D model. Towards the end of the process, there wasn't a single surface on the gripper that hadn't been modified to minimize size, maximize strength, reduce mass, improve ease of use, reduce unwanted friction, and increase desired friction. Once the mechanical team fleshed out the design that we needed an efficient programming to bring Ripley to life.
Hi, Pullium. I was the lead programmer on this team. Ripley required over 3,000 lines of pretty compact code. One of the prides of that code was closed loop control, which means constantly getting feedback from sensors. Believe it or not, most undergraduate robots are done with open loop control, meaning that they drive blindly for a certain amount of time or until a sensor is tripped. That wasn't good enough for us, so we spent a lot of energy trying to figure out how we could have Ripley constantly updated with sensory information as she traversed her environment. So almost all of the actions that Ripley does are closed loop control. I'll show you a couple examples of those. One example is our PID controlled navigation. There's 2 sonars on each side of Ripley, and those update every few milliseconds or so that she has some translational awareness in 2 dimensions, and because there's 2 sonars on each side, she also has rotational awareness to make sure that she's squared up on approach. Another example of closed loop control on our bot was our gripper assembly. Probably the easy thing to do would just be to write the servos to a known position and assume that at that position they could hold the blocks, and as it traveled around the board, it would keep that position and the block wouldn't fall out due to turbulence. But we wanted to do things the right way, and so we implemented a PID controller by measuring the current required to create the proper amount of torque on the blocks. And so Ripley has current sensors for each servo that are constantly updating the current and therefore her ability to grip the block or the amount of pressure she has on each block. One of the most challenging aspects of the programming team was SPI communication, serial peripheral interface. It was the method that we used to communicate between our main master board and 11 slave microcontrollers. And we have to do this by creating a protocol where we send byte packages that are encoded back and forth. So an example of that would be the gripper slave trying to communicate with the master slave, and in just 8 bits in the bit package that it has to go between, we've encoded messages like, we're holding the blocks, we're ready to leave the bars because we have a strong grip. And then also, encoded in each byte is the colors associated with each finger, with each servo that it's holding, so that the master board can know when to release those certain blocks. In my professional and educational experiences, I've been on a few teams that demonstrated this level of collaboration, and we're very proud of all the things that we learned, our growth and our ability. We're also very aware of our weakness in long-term time management.
That's always the problem.
The learning gains from this assignment, can't stress enough, we all feel the same way, was equal to or average to a whole semester of regular engineering classes. We got to take the theoretical that we learned so well and then realize that the theoretical is great, but bringing it into practice is a whole nother ballgame. And most engineers don't have that experience until they're in the real world. Great thing about UNCA students is we like each other to succeed and share that information. So you're going to see those educational gains in junior designs and senior design classes and in other mechatronic endeavors. We want to reward the department for their investments, and we plan on completing most of the functions of Ripley and giving it to the Mechatronics Ambassadors Program to use as an outreach tool. We'd like to thank UNCA, especially the engineering department and the students, for all of your support and the opportunity. And with that, if we have time, we'd like to open the room for questions.
Actually, I don't think we do.
Okay.
And I understand you're going to have a demonstration.
Yeah.
So since we're behind time, let's thank our team. Are you going to be there after the session is over as well?
We're just going to head to room 103 next door if it's still open and do like a 2-second, 3-second demo of driving up to the bar.